Okay, so we are on page 1 of your new workbook. If you are at home watching this and you do not have, or at school watching this and you do not have a workbook, come and see me and get one, okay? I think most of you do, but just in case. So the nature of gases. Gases have something that starts with M. Mass. Yes, they have mass. And that's because they are made of something that starts with P, particles. And since particles have mass, therefore gases have mass. Gases are something that starts with C. Compressible, yes. Nailed it. Woo. They are compressible. Oh, that's a big word, hardly fits on there. They are mostly compressible. Unlike liquids and solids, solids cannot be compressed. A lot of people think that liquids can be compressed, but they cannot. Okay? So they are mostly, oh no, that shouldn't say mostly compressible. It should say they are mostly empty space. Yes, thank you. Unlike solids and liquids, therefore they compress easily. Just gonna go get the door. Okay. Gases fill their containers completely. So if you want to know the volume of the gas, you just have to know the volume of the container. They do not, what do they not do? They do not settle to the bottom. Oh, I did not leave enough room for that. More room. Okay. They do not settle to the bottom of the container like solids and liquids. Gases, what do they do? Let's see, they move through each other rapidly. Because they are mostly empty space, the little gas particles of one gas can go through the gas particles of another gas. What do we call that process where gas particles move through each other and mix? You're close. Diffusion. Okay, so when they move through each other and mix, that is called diffusion. And this leads to the complete mixing of gases, forming a what kind of mixture? Homogeneous, yes. Gases exert pressure. This pressure is due to the gas particles frequently doing what with the walls of the container? This is our little container here. This is a little gas particles. What causes it to have pressure? What do the gas particles do to the walls of the container? They're moving, and as they move, eventually, what do? They collide with the walls of the container. So if you imagine a balloon, the reason the balloon stays, its nice balloony shape is that because those gas particles are bonking into the outside of it, or the inside of it rather, and pushing outward, okay? So that's what pressure is. It's gas particles colliding with the walls of the container. What do gases do when we heat them? So if I had a gas and it was in a container and that container had a piston, do you guys know what a piston is? It's like a little movable uppy downy lid kind of thing. Does that make sense? A movable uppy downy lid kind of thing? Okay, that's a piston. And so if we have a piston and we have some gas in here and then we heat the gas, what will happen? Yes, it will expand, okay? That wasn't, I want it to be more obvious that it has expanded, so we'll make the little piston movie uppy downy thing go there. So the particles take up more space as they move. How are they moving? Faster. Do you have a book? Do you need a book? Okay. I was wondering why I have so many. I'm like, good Lord, I've got a lot of these things. Here you go. And there's an answer key. Anyone here need an answer key? Yeah. All right. So our little particles in here, they're moving, but they're moving quite slowly. But these ones are moving faster. Wah! And so that causes the pressure to increase, which causes the space to expand. All right, gases exert comparatively how much pressure upon heating? Do they exert more pressure or less pressure? More. So as the particles move faster, what do they do with the walls? They collide with the walls more frequently, yes? Yes, with more force or more energy, either way, with more force. So if we had, instead of a piston, instead of a movable piston, if we had a lid that's just locked in place, and we've got our little particles and they're moving slower, and then we heat it, because that is an immovable lid and it cannot move, all that's going to happen is that you'll have these same four particles, but they will collide more frequently and with more force because they are moving faster. Whee! And that is 13.1a. Is good? Moving on, 13.1b, page 2. There's a couple of videos here. You are welcome to watch them on your own if you feel like you don't get it from what we do here. Okay. Do you remember learning kinetic molecular theory in grade 8? A little bit? It's been 100 years, right? Or three years, okay? So Kinetic molecular theory, in terms of what we're looking at, it explains why gases behave as they do. The postulates, isn't that a fantastic word, postulates, which are the main concepts of KMT. What does KMT stand for? Kinetic molecular theory. Gases consist of very small what? Particles. Each of which has mass, which are in, yes, constant will work. I had continuous, but constant also works. Constant, random motion. Okay. So that's basically what we were talking about in the previous thing, is they're particles, they have mass, and they're in constant random motion. The distances separating gases are very large. Okay, they are extremely, extremely big. And what that means is that the actual volume of the gas molecules themselves, I should put themselves in here. Okay, the actual volume of the gas molecules themselves is what compared to the total volume of the gas? It's very, very small. It is insignificant. Ooh. Compared to the total volume in which the gas is contained. Ooh, another word you could use there, negligible. Ooh, another nice one, negligible. And the reason I'm bringing those up is we will be using the terms insignificant and negligible a lot in Chemistry 12, because we do make some assumptions that we assume that certain changes in quantities are insignificant or negligible. All right, attractive and repulsive forces between gases are, now I want you to think about this, the distances separating the gas molecules are very large, therefore the attractive and repulsive forces between gas molecules are very negligible, they are very small. Yeah, no, they are very, very small, so they are negligible or insignificant. Negligible. Very small. Okay. Now, collisions between gas molecules are considered to be perfectly, now I don't know if you'll get this one or not, depends on how much physics you've done. Collisions are perfectly elastic. And so if they are perfectly elastic in an elastic collision, if you've not heard this, it doesn't mean that, it's made of rubber or anything like that. And in fact, it is one in which no kinetic energy is lost. In other words, gas molecules can transfer kinetic energy to one another when they collide, but no kinetic energy is transformed into any other forms of energy. So the funny thing about an elastic collision is, let's say you have a rubber ball. You would feel like that's kind of elastic because it's squishy, yes? Well, that's not true at all. Like if you have an elastic, if you have a rubber ball and it bounces, it will, you know, when it hits the ground, your rubber ball will squish. Yes, a little bit before it bounces up again, right? We get that little squish at the bottom. That squish, that deformation, is going to cause the particles in the ball to move and then move back to where they came from as it unsquishes, and they'll be moving faster. And so now you'll have lost some of that translational kinetic energy, and it'll be transformed into heat energy. Okay? So those are not actually like an elastic ball. A rubber ball is not actually elastic. The closest thing that we can think of as an elastic, mostly elastic collision is billiard balls, like pool balls, because they are very, very hard, and they basically transfer all their energy to the next one when they collide. Okay? So if something squishes, the collision is non-elastic. If it does not squish, the collision is elastic. Do you have a rubber ball? Oh, very cool. How timely. All right, so the average kinetic energy of the gas molecules depends upon what does it depend upon? Temperature. Because of course, temperature is, what is temperature? It's a measure of the average kinetic energy. Like literally, that is the definition of temperature. It is a measure of the average kinetic energy of the particles. So literally, that is the definition. So if we have a higher temperature, we have a higher kinetic energy. If we have a lower temperature, we have a lower kinetic energy. And that's it for that one. Whoa, we're just screaming through today. I know, right? All right, pressure barometers and manometers. So if you are wanting to look at something on this and you're like, Miss Fence's diagrams are not so nice, you can refer to our big black book, which the BLB, which is online, of course, on Teams. You can read that if you desire, okay? And if any of you in grade 12 would like to have a copy of said large book, let me know and I can get you one. All right, pressure of a gas is the something that the gas exerts. A force. Yes, it is a force that the gas exerts on a unit of surface area. Yeah. Or you could just say area. So mathematically, P equals F over A, where P, what does P stand for? Pressure. F stands for force, and A stands for area or surface area. Yeah, the gas part does involve some physics. And in fact, it used to involve a little bit more physics, but they took out some of it. We used to use 1/2 mv squared to calculate speeds of particles, or the kinetic energy of the particles. All right, there are different units of pressure. Do you remember these from the gas little thing over Christmas? There were atmospheres, which is abbreviated ATM. There are torr, which is abbreviated torr. There are kilopascals, abbreviated kPa, and millimeters of mercury, abbreviated mug. M&M? Now, the conversion factors, and these are actually given to you on your AP data sheet. Now, I don't know what you have on your current sheet. What I will do is I will grab you a new sheet that has the gases stuff on it if you don't have it. Does one of you have your? Yeah, no, you guys need a new sheet. So, people at home, you will want to drop by my classroom and pick up a new AP sheet that has gases on it as well. Okay, 1, 2, 3. Okay, here, I'll just hand these out real quick. So, there we go. Yeah, if you want to take some for other people, feel free. You want to take.
Do you think like Daniel needs to want?
One, two, three, four. Yes, you can. There we go. Anyone else want more? One more. There we go. Anyone else?
No, wait.
Do you know one more? I do need 2 more. You can just return any that you don't need.
One to Oliver, Daniel, Eric.
Okay, and if there's any you don't need. So some of you at home, you're being taken care of. Your friends have looked after you, all right, and are bringing them to you. If you don't get one from a friend today, just drop by and pick one up from me. I will put them on our little table at the back of the room, so you don't even have to see me to go get it. Okay, but on this table, which sadly I have not actually put up on our notebook yet, on the back of it, there is a section on gases, and it tells you that 1 atmosphere is equal to 760 millimeters mercury, which is equal to 760 torr. And I don't think, it does not give you kilopascals, so I'm guessing that you will not be required to do anything in kilopascals. You can tell this came out of the States because kilopascals is the metric unit for this. It is equal to 101.3 kilopascals. We might use that, so if you would like to write that onto your sheet, you may do so. Yeah. Because I think some of my questions might involve kilopascals because it did used to have it in previous versions. This is 1 atmosphere is exact. Okay, that's like a definition. And these are all the pressure of the atmosphere at sea level. Okay, 760 torr, that has 3 sig figs. 760 millimeters of mercury has 3 sig figs, and 101.3 kilopascals has 4 sig figs. Okay. Oh, and look, I wrote this here. These are all the atmospheric pressure at sea level, which is fairly close to what our pressure is because we are very close to sea level. Okay. Atmospheric pressure occurs because air has, yes, sorry. Because it's 760 plus or minus 1, not 760 plus or minus 50. Okay. As we move into grade 12 in university, usually if you have something ending in a nice number and it's in the hundreds, it'll probably be to the ones position. Okay. Yeah. Yes. Because we don't. Yeah. I'll double check on it for you just to make sure. Anyway, we are done for the day. There's no homework. Yes, you have a question? Huh? No, I don't think so. I'll check. I'll check for you. I'll check on the sig figs. So hold your horses on the sig figs. I will double check for you and make sure I get the correct scoop. Alrighty? No homework because you have enough to do in semester 2 without me assigning you things. There might be a little something over spring break, but not too much. Okay. Absolutely, totally fine. Yeah.